Now we're going to look at a return to the gas laws, the experimental basis, and how to determine which of the laws to use. So, gas laws, the experimental basis. The goal was to understand the basis of the gas laws, and we showed you the basis by giving you a couple of demonstrations, and know how to use those laws. So we're going to learn now how to use those laws. So these are the 5 basic laws that you're going to have to use: Charles' law, Gay-Lussac's law, Boyle's law, the combined gas law, and Avogadro's hypothesis. And there's a lot there to remember. And it's a lot easier to do because I don't care if you know the name of the law. I just care that you use the correct one at the right time. So I want you to remember that the ideal gas law is PV equals nRT. So here I have a gas under one set of conditions, P1, V1, N1, and T1. And here I have this gas under a different set of conditions, P2, V2, N2, T2. You'll notice the number of dots here does not equal the number of dots here because N1 and N2 have changed. Clearly the volume has changed. Presumably the pressure has changed. I can't really show you that the temperature has changed. I don't know how to make one of them hot and the other one cold. I guess I could draw like snowflakes on one of them, and I can draw like flames coming off the other one, but I can't. I'm not a good artist. So I want you to recall that from the ideal gas law, if PV equals nRT, then for this first cube, we have P1 V1 is equal to N1 R T1. Why does the R not have a 1? Because the R is a constant. It does not matter whether the gas is here or here. R is R. Now, what about the second set of conditions? We have P2 V2 is equal to N2 R T2. Now, when we solve this equation for R, we get P1 V1 over N1 T1 is equal to R. When we solve this equation for R, we get P2 V2 over N2 T2 is equal to R. So that means that P1 V1 over N1 T1 is equal to P2 V2 over N2 T2 because they're both equal to R. Well, this happens to be Boyle's law, Charles' law, Avogadro's law, or hypothesis, the combined gas law, and Gay-Lussac's law all in one. This one formula is the equivalent of these 5 formulas. So do you want to remember these 5 or this one? I'd rather remember that one. Let me show you how we can use this formula to get Boyle's law, which is P1 V1 is equal to P2 V2. So Boyle's law from P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. For Boyle's law, there's a change in pressure and there's a change in volume, but there's no change in moles. So that means that N1 is equal to N2. And there's no change in temp. So that means that T1 is equal to T2. So we can change this formula and keep the left the same, P1 V1 over N1 T1. But on the right, I'm taking N2 and I'm writing N1 because N1 is equal to N2. And here, since T2 is equal to T1, I can write T1 on the bottom here. Now, when you have this formula here, what happens when you multiply this side times N1 T1? Well, you have to multiply the other side times N1 T1. And what happens to N1 T1 and N1 T1? They cancel and they cancel. So this simplifies into Boyle's law. P1 V1 is equal to P2 V2. We simply have to remove the variables that don't change, and we have the law we need. So let's look at using the right law. Basically, there's 2 laws. There's P1 V1 over N1 T1 is equal to P2 V2 over N2 T2, and there's the ideal gas law. So the first thing you do when you look at these equations, you ask yourself, does any of these change? If the answer is no, you have a static situation, use the ideal gas law. If the pressure changes or the moles change, or the volume changes, or the temperature changes, you've got to use this formula. When you use this formula, you remove the variables where there's no change, and you get the law that you need. So let's take a look at this applied to some problems. So they tell us that this one is Boyle's law, but we don't care about that. So I'm going to move this up so that we can't see that. A bicycle pump has a volume of 1,400 centimeters cubed. If a sample of air in the pump has a pressure of 730 millimeters of mercury, what is the pressure when the volume is reduced to 460 centimeters cubed? Oh no, I'm now frightened because I haven't seen these volume measurements before, centimeters cubed. I thought they were supposed to be liters. Let me show you what's really neat about doing a problem like this. So first of all, can you see that if I call that V1, I've got 1,400 centimeters cubed, and it has a pressure, so that's P1 is 730 millimeters of mercury. And here, what is the pressure when the volume is reduced to 460? So I have a V2, 460 centimeters cubed. And here it says, what is the pressure? So that presumes there is a new pressure. Now, if the sample of air is in the pump, and then we just change the pressure, what happens to the amount of molecules in the sample? It doesn't change. So N is constant. And here they don't say anything about the temperature, so we assume that the temperature is constant. So here, since there's a change in volume and a change in pressure, we're going to use P1V1 over N1T1 is equal to P2V2 over N2T2. Secondly, since N is constant as T is constant, we just take these variables right out of the equation and we get P1V1 is equal to P2V2. Now, since P2 is what I want, I'm going to rearrange this equation so I have P2 on one side and everything else on the other. So I get P2 is P1V1 over V2. And now it's a simple matter of plugging the numbers in. Now, I'm still concerned that these are volumes that I'm not used to, but let's see how this plays out. So P1 is 730 millimeters of mercury. V1 is 1,400 centimeters cubed. And V2 is 460 centimeters cubed. And I'm thinking to myself, well, wait a minute. These are not volume units I'm used to. However, it's centimeters cubed over centimeters cubed. What happens to those units when they're the same on the top and the same on the bottom? They cancel. So that means our answer is going to be in millimeters of mercury. And we don't need to convert centimeters cubed to liters. Whew, I'm so happy. Now, when we want to estimate this answer, how many times does 460 go into 1,400? 3 times. What's 3 times 730? Around 2,200. So our answer should be around 2,200 here. And let's see what we get. 730 times 1,400 divided by 460, and we get 2,221.7. How many significant figures are we allowed? And the answer is 2. So instead of 2,221, we're going to write 2,200 millimeters of mercury with 2 significant figures. And so we don't care that this is Boyle's law. We got to the right answer just by knowing what changed and what didn't change. Let's take a look at another problem now. So that was a Boyle's law problem. I'm going to scoot this up like this, and we'll take a look at the next problem. So here's the next problem. it says the law right here in the corner, and you can't see it, and that's on purpose. So a sample of CO2 in a gas-tight syringe, as in the figure, so, well, we better draw a figure for that, has a volume of 25.0 milliliters at room temperature. What is the final volume of the gas if you hold the syringe in your hand and raise its temperature to 37 degrees Celsius? Okay, so we have a syringe, and here's the plunger. And we have a volume of 25.0 milliliters. So V1 is equal to 25.0 milliliters. Now you might be thinking, well, how do we know there's a V2? And why would you even write a V1 if you don't know there's a V2? And the answer is really simple. I'm going to go ahead and write V1 because when I'm writing down the rest of this information, if I only get ones, V1, T1, N1, P1, and I don't get anything else, there's nothing changes. I use the ideal gas law. So I'm just setting myself up just in case there are changes. So this is my CO2 gas in an airtight syringe with a volume of 25.0 milliliters. Now it's room temperature. So I don't want to write 20.0. I want to write 293.15 K. And the reason we want to do that is because we don't do gas problems in Celsius. We do them in K. Now, what is the pressure of this syringe? We don't know. How many moles of gas are in this syringe? We don't know. So I'm going to write N1 is equal to whatever, and P1 is equal to whatever. Now, notice here, this says, and hold the pressure constant. Wow, that's going to help me out a little bit. So we hold this in our hand and we warm up the gas. So the final temperature of the gas is going to be a little higher. Now, what do we think is going to happen when we warm up the gas? I think that this syringe is going to move further away or make this volume larger. So I'm going to have V2, and it says, what is the final volume? So that's V2. And when they give us a V1 and they say, hey, what's the new volume? You know right away it's a dynamic problem. So T2, we're not going to write down 37. We're going to do 273.15 plus 37, which I believe is 310.15. Let me double check that. 273.15 plus 37, 310.15. Now this is only good to the ones. It's kind of interesting here. This is only good to the ones, and this is good to the 10th. You would think that they would be both good to the 10th if you're using the same thermometer, or both good to the ones. So this is an interesting concept here, using different thermometers for the same problem. And here, N2 is equal to, well, we don't know, just like we don't know N1, but the amount of gas in here, the dots, presumably are the same. So I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, same number of dots. So I can say it's equal to N2, and that's equal to N1. And finally, we have the pressure. The pressure is constant, so we don't know what the pressure is, but we know that P1 is equal to P2. So these guys stay the same. And if they stay the same, what do we do when we have that equation? We remove them. So what is that equation again? Let's take a look. The equation is P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Since moles stay the same and pressure stays the same, we just get rid of them from both sides. So now we have V1 over T1 is equal to V2 over T2. Oh, did you see the mistake I did here? That's supposed to be a 2. All ones on this side, all twos on that side. And here we want V2. So when we rearrange this, remember the little cross multiplication where we say V2 times T1. V2 times T1 is V1 times T2. And then how do we isolate V2? We divide each side by T1. And then we just plug and chug. So V1 is 25.0 milliliters. Now, this is where many students make a big mistake. Do you see that that's T2 and that's V1? Many students put V1, T1 because it just seems to go together, V1, T1. That's not T1, it's T2. So we have to use that temp. Divided by T1, which is 293. So make sure that when you have this formula written correctly, that you substitute the right number for the particular variable. T2, 310. T1 on the bottom, 293. V1 and T1 don't belong together on top. So I'm going to estimate the answer. Can you see that 310 divided by 293 is a little bit bigger than one? Squish more, right? So the answer should be a little bit more than 25. And I'm going to guess that it's about 20, well, either 26 or 27 for a final answer. All right, let's see what we get here. We get 25 times 310.15 divided by 293.15, and we get 26.4 milliliters. And that is the final volume. And sure enough, when you hold it in your hand, the volume does increase very slightly. Now, it's kind of interesting when you take a look at the temperatures. The temperatures were 20, and then it increased to 37. So the temperature essentially doubled. So why doesn't the volume double? Well, because the temperatures are supposed to be in Kelvin, and it doesn't double. It goes from 293 to 310, which means it increases by about 5%. So what is 5% of 25? Well, it happens to be about 1.4. Okay, so here we ended up using this equation right here. Oh, what did I do here? Oh, that's my cross multiplication. So we ended up using V1 over T1 is equal to V2 over T2. And if we go back and take a look at all of the different problems we have here, you see that. Let me see. Here we go. You can see that that one is Charles' law. So this appears to be a Charles' law problem. Well, let's take a look and see if indeed it was. So, and there it is. It's a Charles' law problem. Do we need to know the name of the law to be able to do it? No. So let's take a look at yet another problem. Okay, so this one, we're going to give it a try. Helium-filled balloons are used to carry scientific instruments high in the atmosphere. Suppose a balloon is launched when the temperature is 22.5 degrees Celsius and the barometric pressure is 754 millimeters of mercury. If the balloon's volume is 4.19 times 10 cubed liters and no helium escapes from the balloon, I wonder why they're telling me that. If no helium escapes, that means that no moles of gas escape, which means the mole stays the same. Okay. What will the volume be at what will the volume be? They give me a volume here and they say, what will the volume be? That's a change in volume. So right away, I know I want to use P1V1 over N1T1 is equal to P2V2 over N2T2. And here they say that no helium escapes. So I'm going to get rid of the N's. And I'm going to start making a list of the things that they give me. So T1 is equal to 22.5 plus 273.15 K. So when I add those together, I get 0.65 and I get 295.65 K. The barometric pressure, so that's P1, is 754 millimeters of mercury. And the volume, V1, is equal to 4.19 times 10 to the third power liters. What will the volume be at a height of 20 miles? So I'm going to put V2, this is what we want, where the pressure, P2, is 76.0 millimeters of mercury. And the temperature is minus 33. So T2 is negative 33.0 plus 273.15 K. Let's add those together. So here we're going to get 0.15, and 3 minus 3 is 0, and 7 minus 3 is 4. So 240.15 K. And I'm bad at adding and subtracting, so I'm just going to double check. 33 negative 33 plus 273.15, 240.15 K. So now we're going to take this, and since we want V2, we're going to get V2 is equal to P1V1 times T2. So P1V1 times T2 divided by P2T1. Whew, there's a lot of subscript in there that we need to keep track of and put the right number in the right place. So let's do it. P1, 754 millimeters of mercury. V1, 4.19 times 10 cubed liters. T2, that's over here, 240.15 K. So I'm going to double check. P1, sure enough. V1, sure enough. T2, sure enough. Divided by P2, 76.0 millimeters of mercury. And T1, which is there, 295.65 K. So can you see that the millimeters of mercury cancels with the millimeters of mercury? The K cancels with the K, and we're going to be left with liters as our final answer. And if we think about significant figures here, this is good to the 10th. This one is also good to the 10th. This has 3 zig figs, 3 zig figs, 3 zig figs. This has 4 and 4, so we're left with 3 significant figures. Now, as I try to do this problem, here's what I'm going to do. That goes into that one time. I know it's not 1, but it's close. That goes into that 10 times. 10 times 4.19 times 10 to the third is 4.4 times 10 to the fourth. Okay, now it should be close to 4 times 10 to the fourth, but I know that this doesn't go into that one time. It's less than 1. So I'm going to say that the answer is probably going to be more like 3.8 times 10 to the fourth liters. Okay, so 754 times 4.19 second EE3 times 240.15 divided by 76.0 and divided by 295.65, and we get, I'm going to put this in scientific notation, we get 3.38 times 10 to the fourth liters. And I said something like 3.8. Not a very good estimate there, but I did say 10 to the fourth. So here's this problem. Now, which gas law did we use? Well, they call this gas law in our book the general gas law. I call it the combined gas law. Did we need to know whose law that was to be able to use it? The name of it? Nope, not one bit. Okay, let's put that off to the side. And now let's take a look at another problem. And I think this is the last problem we're going to look at for this section. Let me see if there's another one underneath there. Nope. So this is the last problem. So we don't know whose law we're going to use. Dinitrogen monoxide, commonly known as laughing gas. So I'm going to write that down. Dinitrogen monoxide, commonly known as laughing gas, is used in dental procedures as an anesthetic. At elevated temperatures and with the proper catalyst, dinitrogen monoxide can be produced from the reaction of ammonia and oxygen. So here's ammonia, here's oxygen producing laughing gas and steam, as it were, or water vapor. If you begin with 15 liters of NH3, so 15.0 liters, that's going to be the volume. And since they say begin, I'm going to call that V1. What volume of O2 is required for the complete reaction of both gases being at the same temperature and pressure? What is the theoretical yield of N2 in liters under the same condition? So this is a pretty interesting question. Now, one of the things that I want to teach you here is this, that these coefficients are moles of reactants. So this is 2 moles of NH3 reacts with 2 moles of O2 to give you 1 mole of N2O and 3 moles of H2O. So we all know that that's what the coefficients mean. They mean how many moles. But I want you to remember that when we look at the ideal gas law, PV equals nRT, we can see that N is proportional to P, N is proportional to V, and we're not going to worry about temp because here we got the same temp, the same pressure. So here we're going to look just at this, N is proportional to V. And if that's the case, and these here are just ratios, I can actually think of this differently. I can think of this as 2, let's see, they're using liters, 2 liters of ammonia react with 2 liters of oxygen to give you 1 liter of N2O and 3 liters of H2O. And this works because moles and volume are proportional. You see how they're both in the numerator here in this equation? When they're on either side of the equation here, that means they're directly proportional. If we keep everything the same and we double the moles, then we have to double the volume. Okay, so here we have these new conversion factors. So if you begin with 15 liters of ammonia, what volume of O2 is required for the complete reaction of both gases at the same temp, or excuse me, complete reaction, both gases being at the same temp? What is the theoretical yield of N2O in liters under the same conditions? So first of all, I'm going to calculate the volume of O2. So the volume of O2 is going to be 15 liters of NH3 times, and take a look. Since I want to know the volume of O2, I can write 2 liters of O2 over 2 liters of NH3, because the mole ratios are 2 to 2, 2 to 2. The liter ratios are 2 to 2. So the answer is 15.0 liters of O2. Now, how do we get the volume of N2O? Well, that's going to be 15.0 liters of NH3 times, according to this, 1 liter of N2O per 2 liters of NH3, which ends up being half of that, which is 7.50 liters of N2O. So it turns out that this is not really anyone's law. There's kind of a clever way to do this. They call this an Avogadro's hypothesis. So if you look at Avogadro's hypothesis is the relationship between pressure and temp. Oh, I'm sorry. It's a relationship between volume and moles. That's Avogadro's hypothesis, if I'm correct. Yeah, I'm correct. So what they want you to do in this problem actually is they want you to first calculate what the volume is of, actually with the volume here, how many moles of NH3 you're going to use, and then calculate the moles of O2, and then calculate the volume. So they want you to do 2 Avogadro's hypothesis type problems, and we can do that. So let's take a look at what they had intended for you to do, which is really kind of a hard work. So we would do this for the NH3. We would say V1 is equal to 15.0 liters. And we'd say that N1 is equal to, we're just going to write 2.0 moles because we're taking that from that equation right there. All right. So what volume of O2 is required for the complete reaction? So we know that V1 over N1 is equal to V2 over N2. And so they want us to use these numbers here. Oh, you know what? I don't even want to do it. So what is your lesson here about these coefficients? The answer is those coefficients could be pressures. Those coefficients could be volumes. Those coefficients are definitely moles. But I want you to be aware that when you have constant pressure, so here's the deal. At constant pressure, the coefficients are volumes. And at constant volume, the coefficients are pressures. So when I say that they're volumes, what type of volume? Whichever one you want. Liters, centimeters cubed, milliliters, whatever is going to be most useful for you. And at constant volume, the coefficients of pressure. What type of pressure? Well, atmospheres if you want, or millimeters of mercury if you want, whatever's going to help you. And that's how you do that problem. So it's kind of a clever little problem. All right. Thank you for listening, and check out the next lecture.